A very good morning to all. Our next topic is image enhancement in the frequency domain. In the previous section, we have seen enhancement using some of the spatial domain techniques. Here, we will see some transform or frequency domain techniques. So, starting with fundamentals, we have Fourier, which is nothing but the periodic function that can be represented by a sum of sines or cosines of different frequencies multiplied by coefficients. Now, non-periodic functions are generally represented as an integral of sines or cosines multiplied by a weighting function. This is a small example of a Fourier transform for a given image f of x comma y. Now, this is as the size of the box increases, we can see that as the size increases, the variation that is observed in our transform domain. Now, this is the first one-dimensional discrete Fourier transform expression for f of u and f of n, that is for the forward and for the inverse DFT. These are some of the examples for n is equal to 4. So, f of u is complex even though f of n is real. Now, DFT requires at least of the order of n square computations where n is the length of the sequence. Then came up the FFT or the fast Fourier transform. The fast Fourier works best when n is equal to the power of m. The radix 2 algorithm is most commonly used. The computation complexity of radix 2 FFT is n log of n adds and half n log of n multiplies. So this is the computation time required for FFT algorithms. Coming to two-dimensional base DFT, which we will be applying for images, the Fourier transform is suitable for continuous domain images which may be of infinite extent. For discrete images of finite extent, the analogous Fourier transform is the two-dimensional DFT. Now here we have a two-dimensional function, so f of u comma v, and the expression for the two-dimensional DFT transform. The inverse DFT, two-dimensional DFT, is given by f of m comma n. The MATLAB function FFT2 implements a two-dimensional DFT by the use of one-dimensional FFT. So when we implement it using MATLAB, the function that could be used. An example of the original image, the absolute value of f of u comma v. So for a given image, how the transform domain looks like is indicated here. Some of the properties of two-dimensional FFT, that is similarity, separability, it has linearity, you can obtain the DC coefficients, and image enhancement in frequency domain methods. Now, an enhanced image is obtained by the convolution of PSS, that is point spread sequence, with that of the original given image. So, in the frequency domain, we represent as enhanced image is equal to the transfer function multiplied by the given image. So, here also we can see that we have low pass and high pass based filtering techniques. Edges and sharp transition gray levels is an attribute that contribute significantly to high frequency content in its Fourier transform. Now, ideal low pass filter, its representation is h of u comma v with a cutoff frequency of R0. This is an example of MATLAB coding. Ideal low pass filter example. This is an output response of an LPF filter. So we notice that the several ringing effect in the blurred images, which is a characteristic of ideal filters, and it is due to their discontinuity in the filter transfer coefficients. The ringing effect can be visualized in this way. First is a frequency domain low pass filter that is considered of radius 5, corresponding representations in the frequency and spatial domain are indicated. And the most important point as we use the filters is the cutoff frequency. So an ideal cutoff frequency is required so that the filtering is more accurate. So one example of a low pass filter is a Butterworth filter. The expression for the Butterworth filter is given here. Butterworth low pass filter response. An example of a MATLAB function for the implementation of the filter, Butterworth filter. So we find that there is a change in the ringing effect as we change the order or the filter order. So there are some variations as we observe for different order of the filters. There are also other filters like Gaussian low pass filters. The effect of Gaussian low pass filter on an original image. High pass filtering can also be carried out for our images. Some of the examples: h of u comma v with the cutoff frequency of R0, and ideal HPF with R is equal to 15. So here also we observe the severe ringing effect in the output is a characteristic of ideal filters, and it is due to the discontinuity of the filter coefficients. Again, a Butterworth high pass filter. A response of Butterworth high pass filter. Now we pause here for a moment and please students work out an example. Consider an image of your own. Work out the difference between the spatial domain filtering technique and the frequency domain filtering technique and see what is the difference that you can observe for the two images. Also work on different types of noises that are available in the image and submit it as an assignment for next week. Thank you.